So, with all the things that we have described from Unit 1 to Unit 4 Part A, which we completed during all the last lectures, the last we concluded Part A of Unit 4. We are continuing with applications of partial differential equations, and now what we are going to take is the heat equation, details of it. Then we will be coming to boundary value problems again. We will be doing the initial value problems. So, we start with the application of partial differential equations to heat equations. Before that, we had done, if you remember, D'Alembert solution of partial differential equations. We start with unit dimensional heat flow or one dimensional heat flow. The heat flow in a body of homogeneous material is proportional to the gradient of the temperature. That is the basic concept of the heat flow, and therefore this whole concept is written in an equation form: small v, this is vector notation, minus capital K, this is what we call as the del capital U. This usually we use in vector calculus notations, where small v is the velocity of heat flow. This bar on the top of every quantity will denote the vector. The diagram or the figure which we have drawn is very simple. We are going to explain these in the next part. We call this as the body, and U, X, Y, Z, T is the temperature at the time T, and K is a positive constant which we call as the thermal conductivity of the body. So, X and Y are variables, Z is a variable, T is the time, and K is a positive constant which we are using. We consider a volume V in the body and let S is its surface. That is what we have drawn in the figure, this figure which we are going to explain. This is small v, as you can see, going up with the arrow. Capital V is the volume enclosed in that diagram. ds is the small part of the area, and n is the outward drawn normal that we have here. So, we say total heat leaving capital S per unit time is given by double integral on the surface capital S. V dot n cap means unit vector, and what we have V arrow is called as all complete vector, where n cap is the unit outward drawn normal vector at the surface S shown in the figure. From Gauss's divergence theorem, there are few theorems in vector calculus of which we are all aware of. The fundamental is Gauss divergence theorem, then we have Stokes theorem, then we have line integrals, and then we have volume integrals, etc., which we will be using here. So, from the Gauss divergence theorem, we know that normal surface integral of the function f arrow means vector f is equal to the volume integral of del dot vector f. Del dot vector f is called as divergence of the vector. If it is only del f, then we call it gradient, and about del cross we call it curl. If we come across, we will explain at that particular point of time. So, del dot f, in other words, it is the gradient taken over the whole volume, is given by this equation marked as equation number 2, double integral taken over S of all these quantities is equal to the volume integral. Triple integral always denotes the volume, is del dot vector V, del dot is again divergence of it, minus capital K, triple integral V means volume integral, del square capital U dx dy dz, 3 integrals and 3 variables that appear here. Therefore, the heat leaving that surface area S per unit time is given by equation number 3, written as minus K triple integral taken over the volume V del square U dx dy dz. Let H is the amount of heat in the surface area capital S, and so we can write here with these notations as capital H is equal to triple integral V sigma rho u appearing in equation 3, even in equation 2 and 1 as well, dx dy dz, 3 derivatives because there are 3 integrals, where sigma is called the specific heat of which we know and rho is the density of the body. Need not to explain these two terms called as specific heat and density. Hence, the rate of decrease of H, rate of decrease, that means with respect to the time, is given by, so it will have a partial differentiation, is minus dH dt is equal to minus of triple integral V. We substitute that values and it becomes rho sigma partial du with respect to dt dx dy and dz. Then we have the same simplified. In place of rho and sigma, we put this k and du dt as well from equation 2 and 1, and you get this result. We simplify it and we write this is equal to 0 because triple integral volume sigma rho du dt minus k delta square u dx dy dz all taken over this integral should be 0, that we marked with equation 5. Since it is true for every portion of the volume of the body, every portion of capital V that you have seen in the figure, the integrand of 5, the last equation, must be 0 everywhere because it is true for every portion of the volume of the body. So, we write partial derivative of du with respect to the time t is equal to capital K constant, specific heat and then density, delta square u, that is equation 6. We substitute something for all constant, K is a constant, sigma is a constant, rho is a constant, and so we summarize everything and we write all these constant equal to something c square, and this we take in equation 6. So, it becomes therefore, this particular thing, it appears to give you this result, partial du dt is equal to c square delta square and capital U that we have. We go further and here we write, hence from this equation 7, we have in other words du dt is equal to c square, then we have second order derivatives here, d2u dx square, d2u dy square and d2u dz square, 3 dimensional, and so we call it equation 8. In fact, this concludes the definition of the heat equation. Remember, this equation is a very important equation, and whenever we deal with such things that we are going to call as heat equation, we will be dealing with this particular equation given by 8. There are few special cases which we want to do, and in doing so, if you look at here, if there is no flow of heat parallel to z axis, meaning thereby the flow is in plane lamina in the xy plane, then this equation 8 reduces to 9 given by du dt. You can very well understand the z part of it is vanished, equated to 0 if there is no flow in z axis direction. So, du dt is equal to c square d2u dx square plus d2u dy square. The second special case is in the flow, in case it is one dimensional, that is in a bar parallel to x axis, one dimension in a bar parallel to x axis, then going back to equation 8, we find that equation 8 will reduce to du dt c square d2u upon dx square. Since there is no z, no y, only x remains, so equation 10 is the result, is an outcome of all these things. In case the steady state of temperature in a body, then equation 8 from where we have started gives you du dt is equal to 0. The left hand side will vanish, neither it will be d2u dx square, nor it will be d2u dy square, and never we will have d2u upon dz square. So, only this thing becomes equal to and finally we will be having everything equated to 0, that is d2u dx square, d2u dy square, d2u dz square, all partial derivatives are equal to 0, and this equation incidentally is known as Laplace's equation, this equation 11. We also make a note of it that del square is called the Laplacian operator. We have read these in integral transforms also. Will be written as del square will mean d2u dx square, d2u dy square and plus d2u dz square. In the left hand side, if we put u, it becomes 11. If we put any other variable v or w, it becomes, so all these gaps, as you can see in equation 12 in numerator, will be occupied by u, v, w, whatever we want to replace it. Few remarks are very important, vital for understanding the heat equation, the Fourier sine series of which we are aware of. If it is required to expand fx as a sine series, in 0L, where x is lying between 0 and L in open interval, then its expansion is given by fx is equal to sigma n is equal to 1 to infinity bn sine of n pi x upon L. This is the what we call as Fourier sine series given by 13. This coefficient, as you are observing, bn, incidentally is given by this equation, that is equation 14, 2 upon L, integration is taken over 0 to L, function which we want to evaluate given by 13, sine n pi upon L dx, where n varies from 1 to 3 up to an infinite number. Then after defining single Fourier sine series, we have double Fourier sine series. So if it is required to expand fxy as a sine series in a rectangle lying between this 0 is less than equal to x, is less than equal to 0, is less than equal to a, is less than equal to b, because it is a rectangle here, then its expansion will give double Fourier sine series. They are very important within the application and within mathematics as well. So fxy is equal to, there are two summation because it is a double. So it is one integer is m, the another is n, both varies from 1 to infinity, and amn into sine of m pi x upon a sine of n pi y upon x. This is, we are approaching to double Fourier sine series, where this amn, like the other, where bn was defined equal to 2 upon L integral 0 to L, etc. amn is given by this whole quantity represented as 16th equation. And as you know, there are two integrals, one is x integral, the second is y integral. X is called as an outer integral, y integral which you are looking here is called as the inner integral. Fxy is present there, we are representing, and we are going to differentiate, or we are going to integrate it with respect to dx and dy. Since all are constants limits, you can choose whether it is dx or we are going to integrate with respect to y. N and m as usual, 1, 2, 3, 4, 5, 6 up to infinite number of terms. This is an example to illustrate what we have done just now. If both the ends of a bar of length a are at temperature 0 and the initial temperature is to be prescribed function fx in the bar, then find the temperature at a subsequent time t is a problem. I read once again for you. If both the ends of a bar of length a are at temperature 0 and both are at 0, and the temperature is to be prescribed function fx in the bar, fx is the prescribed function to deal with, then find the temperature at the subsequent time t after time t. Here the temperature is given by this function uxt. This notation we have done even earlier. In the given solid, this is governed by one-dimensional heat equation given by 17, k is a constant. Second order derivative d2u dx square and du dt, u is differentiated with respect to time. Since the ends x is equal to 0 and x is equal to a are kept at 0 temperature, that is what the problem is about, or the given condition in the problem is like this. The boundary conditions are given as u 0t is equal to 0 and the function at, that is u of at, is also equal to 0 for all t, that means for all time measured. The initial condition is given by equation 19. We read it as the function of x and 0 will be equal to fx. We go back to equation 17 if you recall. So then the 17 will have the solution of the form. This right hand side we have had in the previous lecture, and we say it uxt is equal to xx t of t, capital T of t. In other words, x is a function of x alone and t is also a function of t alone. X is a function of x alone and t is a function of t alone. That is what we repeat again. In the previous lecture we have done this sentence, this equation exactly in a similar fashion. We now substitute this value of E in equation 17, which we have done. Then it becomes k of x double dash, that is the second derivative, is equal to capital X t dash. T dash is the first prime, this is called as the second prime. Simply solve it, you get double dash upon x alone is given as t dash upon k t, k constant, t as well of course is. Since x and t are independent variables, naturally uxt, relation 21 that we have seen just now can only be true if each side is equal to the same constant. We say that the constant which we are assuming is mu. So that is what we get, equal to mu. If you recall, in the previous lecture we have taken it something as positive lambda square and negative lambda square, and we kept on solving about it. So now we are saying that because of the x and t are as independent variables, the relation 21 can only be true if each side is equal to same constant. Same constant means we say that it is equal to mu. If it is equal to mu, then I will be having from 21 x double dash minus mu x is equal to 0 and t dash is equal to mu k t, small k again is a constant term. Using 18 in equation 20, equation 18 is to be employed in equation 20, we will be getting x0 t t equals to 0, and the second equation will be xa t of t equal to 0. We marked it as 24th equation. I hope this is not very difficult to understand. I employed all the possible steps of calculation, making it easy mathematical approach to the problem. X double dash is double prime or the second derivative, mu is a constant, k is purely constant, capital T is constant, and so this is the time where we have equation 18 will turn equation 20 into this. Now we make a very familiar notation meaning to it. If t of t is equal to 0, that means the t is a function of t alone becomes to 0, we get u is equal to 0, and if t of t is not equal to 0, then the previous equation, that is 24, will reduce to x0 is equal to 0, x of a is equal to 0. These two equations constitute equation 25. We now solve 22 under boundary conditions given by 25. These are called as boundary conditions. We are solving equation 22 under boundary conditions 25. We will discuss 3 cases. The first we begin considering mu is equal to 0. If mu is equal to 0, then equation 22 will readily reduce to this kind of an equation given by 26. Using 25 in 26, we obtain this. 25 in 26, 25. X0 is equal to 0, Xa is equal to 0. In 26, capital X, small x equal to Ax plus B. By using this, readily we have this. B is equal to 0 and AA plus B is equal to 0. If I substitute this, naturally, combine these two equations, they will result into A and B both are equal to 0. Obviously, these two equations when solved. Hence, x of x equal to 0, so that u is equal to 0, and this does not satisfy 19. If you look in the first case, this is the conclusion of the case 1 that we have. If capital X of x, means x is a function of x alone, is equal to 0, naturally u will become 0. If u small becomes 0, will never satisfy equation number 19. Let us see case 2nd and let us witness whether this will give us the satisfactory solution or not. We take mu is equal to lambda square, the solution of 22 reduces to this. Right hand side you can say a e to the power lambda x plus b e to the power minus lambda x if mu is equal to lambda square. Using boundary condition 25, which we have just now used. So, equation 27 will result into this kind of an equation. There are two. One is a plus b is equal to 0 and the second is a e to the power a lambda plus b e to the power minus a lambda. Both these summing together or take a sum of these will be equal to 0. Once again we have two equations here. A plus b is equal to 0. So, that will give you a is equal to minus b. Second equation is a e to the power a lambda plus b e to the power minus a lambda is equal to 0. When you substitute this particular thing, obviously we get a is equal to 0. I hope you have followed here. I am writing b is equal to minus a. So, the second equation on the right hand of this text you can say, I take a common, it will be e to the power a lambda plus it becomes minus because I am substituting b is equal to minus a. So, it will give you minus e to the power minus a lambda is equal to 0. But e to the power a lambda minus e to the power minus a lambda will never be equal to 0, and therefore, the remaining quantity, that is only a, that will give you 0. So, that is how we get a is equal to b is equal to 0, and since a is equal to 0, a plus b is equal to 0 will implement that b is also 0. Simple equations. What we conclude is this, so that capital X of x is equal to 0 and thus u is equal to 0. But again, very unfortunately we write, this also does not satisfy 19. It will never, like the one in case 1. So, we reject also mu is equal to lambda square, as we have rejected mu is equal to 0 in case 1. We come to case 3rd. Both cases are deleted, are avoided, are rejected. We suppose mu is equal to lambda square, but lambda is not equal to 0, which even in case 2nd. So, the solution of 20t is given by this now. From 25, the boundary conditions, 28 reduces to a is equal to 0, and therefore, a cos lambda a plus b sin lambda a is equal to 0 will give you sin lambda a is equal to 0. So, what we do is we have taken b not equal to 0 because otherwise x will be equal to 0 and u will be also 0, and therefore, it will again not satisfy the equation 19. So, what we do, that we have taken b not equal to 0, the reasons are given on the second line as we have read. Now, solving 29, the previous equation, you get lambda is equal to n pi. So, lambda will be equal to this much, n is equal to 1, 2, 3, 4 is a sequence of numbers. So, we say hence non-zero solutions x and is an integer of the equation 22. If you recall, are given by x and x equal to Bn sine n pi x upon A. Very simple equation. Using 30, 23 becomes this equation, where finally C square n or Cn square will be this, and therefore eventually we get 22 solved as 32 and 33. Rather, 32 is the correct answer, is the complete solution, where this capital En which we have included here is this much. We have written En because to avoid writing all these rigid calculations or rigid quantities, made it short, and later on we have written this. So, I believe, and whatever we did is a complete analysis, the mathematical analysis of the heat equation as partial differential equations. The key words that we have read is known to you: Gauss's divergence theorem, then we have said what we mean by divergence, then we have said triple integral, the volume integral, double integral, the surface area integral, and later on we have started solving under boundary conditions the density, the specific heat, everything came together. And it must be told that Gauss's divergence theorem is the theorem which is used for deriving an equation in the process that you have seen to find the definition of the heat equation. We have defined heat equation, we have used notation to represent the heat equation, we have used the Laplacian operator, we have used the Fourier sine series, we have used double Fourier sine series, and with the help of these keywords we could very easily arrive through one example to the application of partial differential equations to the heat equation. So, that completes now all the applications of partial differential equations. Hereafter we will be doing totally a different thing, again very interesting. They are even called as Laplacian operators, the known name, but we will be doing it very differently. So, once again we have learned so many things at this particular juncture of time, and again I must confess that we are now in a position to apply the first order partial differential equations, the second order partial differential equations with the help of many theories of partial differentiation to various parts, such as one we have done here, D'Alembert's, then we have change of variable, then we have parameter changing, and finally we came and concluded the application through heat equations. So, thank you for your attention.